Good morning. Today we consider uh, segment tree modifications and persistent data structures. Before we started, I want to um, tell you about what here is the problem. Here was a problem. We can't improve our complexity to O log m. Look, we just we considered that case that we in each node we have sorted array. For example, here's nodes. Here are nodes of some segment tree, and we can in each node we for example for this node we consider that we contain sorted array. Good example. For example, so and we can't find for O log n in this segment tree count of members that less or equal than some x. So when we do query in our segment tree, when we do some query, we find, for example, 2 to 4. We find nodes that for O log n. We find nodes that corresponding for some segment. This node and this node. In these nodes, then we want to launch binary search in this node, but what we do, we launch binary search only in this array. For example, let x be 5 and 5. Here will be our pointer, and then when we build our tree, segment tree, we just create pointers for some, for example, if we consider 5, and we do merge sort for this array to get this array, we just create pointers for this to this. When we create pointers for compared numbers. We compare in merge sort iteration, we compare, for example, 5 and 4. So we create pointers, and when we launch our выделение вершин, this and this vertex, we just собираем all these pointers, all these we just go through all the vertices, but go through only we launch binary search on only in first node, and then we go only on pointers for some. If we find, for example, 5, we go 5 and 4. Then we go 5. Then here we go 4. Oh, it's 2. And we when we reach our segments, we just take count and for every node in list that we got, we launch iteration. We just count these nodes, count answers for these nodes. Okay. То есть, I mean, we only when we build our tree, we launch merge sort. When we поднимаемся to some vertex, we launch merge sort, and we remember our pointers. Then we if we get some query for some x, we find upper bound using binary search in root node. Then we collect all vertices, all segments, and with steps on links created in merge sort. Okay, it works for all again, and it's and all collected size of all collected nodes will be all again 2, and we get query for O1 for every node. We get answer for every node for in O1 because we go through pointers. Okay, I think that's clear. Так. Okay. Let's consider first modification. Second. Of dynamic segment tree. Of segment tree. Dynamic segment tree. Let's suppose we have sequence like size of 10 to the power of 9. And when we, if we want to create segment tree on this array, we can't do it because it's this number. No, we can't do it fast, quickly, because this number is too large. But if you know that we get that count of queries will be like less than 10 to the 8, 10 to the power of 8, we can create dynamic segment tree. We just initialize our segment tree with nulls. With nulls. I mean, with nulls. And create a segment tree on this array. But there is a problem, because if we have some many nodes, this size of dynamic tree is too large, and we can do implement our dynamic tree and our segment tree not on just array. We can implement it on nodes. So if we get some query, if we know that if we get some query, we just all these elements are null. So if you get some query, we just have only root node, and which corresponded for null and -1, and we create these nodes if we want to. We create nodes if we want to спуститься in these nodes. For example, let array will be 1 and so on 8. So if we want to create, for example, value for 5, for only 5 update, we want to update update element 5, we just create this edge, then we create this edge. Ну, так. 5, да? 5. We create this edge, and then we create this edge. Easy idea. We just create nodes for every query. If we can't go to the some node, we just create it. And how to get query of some node? I mean, get query on some segments. We just do our recursion. We just go through all this. Сейчас, 1 second. Сейчас. Короче, мы просто спускаемся по всем этим нодам, ищем, разбиваем наше дерево отрезков на ноды, и ищем этих нод. И если мы не можем спуститься, то мы просто возвращаем 0. Вот, прибавляем 0 к нашему ответу. Так, а теперь на английском. we just go through all the nodes. Or if we can't to go to some node, we plus null to some answer, to our answer, and that's it. Because all nodes on when we initialize our array equals to null, when we initialize our segment tree. Of course, it works only for this task, this special task, when we get that all the nodes, all the nodes equals to some number, null, for example. So we for implementation, we create structure node. In this node we have TL and TR segment that corresponded for this node. Sum, we create sum, and node to the left child and right child. So, okay, I formally just I'll show you how to implement it. An example. Git code. Where's my problems? So in this example, how to implement update? We just update our sum when we reach some node. We just update in somewhere our sum. Updated by some value. We consider segment tree on semigroup, on abelian semigroup. We just do this. We not do this. Okay, we just can erase it. And what we do? What in here there is some difference in if this node, if left node is null pair, we create this node, and then we do update. Okay, like this. Okay, there's немного отличий. Okay. Теперь, now, it's all again, it's works for in all log complexity, and works for all query log memory. So get some, it's trivial to all log. So it would be better if I prepared some phrases for before seminar. Offline. There is next modification for dynamic for segment tree, offline segment tree. Offline query based segment tree. There is a task. We want to update our for example, we get list of some queries, like and we know поинтереснее что-нибудь 7.7. Это list some queries, list of queries. We know this list, and this kind of task name called offline. And notice that we know all the segments that updated, and that's mean we must update only these segments. Okay, and we just create array. In this array, we contain we place in this container array all these numbers. Сейчас, 1 second, I think about list of what? Of all values. All, not values, all keys. In query list. So we just place it to we restore it to this list, then we sort it, and delete duplicates. We get all the keys that all the indexes that it's updated, and we get some array. We get some array of those indexes. Okay. For example, 1, 3. Okay, we get some vector, and when we get query, for example, 1, 7, we find upper bound and lower bound for this values in this array. It will be 3 and 5, and we get list. When we get list, and we can build our segment tree based on these indexes. That's all, I think. And when we get some query, we just or update in this onlight list, we change only if we get some query that not placed in this list, there is update list of not queries, not updates. But no updates. Just 1 second. Yes, updates. Not queries. When we pull and when we get some query, we just take upper bound and lower bound in this array, and we get, and as we know that that ranges all indexes in the ranges located in increasing order. We just get that if we build our tree on these indexes, on these segments, we get that just null fun, just yeah, before no, we create segment tree based on st array, based on array. And find upper bound and lower bound of upper bound and lower bound. If we get in this array, in a array, and do query, if we get we got query query. Okay, I think it's normal. That's all. Do you have questions about offline query-based segment tree or dynamic segment tree? Or dynamic segment tree? I think I can explain it better on Russian. Давайте я объясню на русском лучше. На второй раз. Короче, если у нас есть массив всех апдейтов, которые мы вот получили какой-то список всех апдейтов, да, и мы знаем, какие значения будут обновляться в этом списке. Дальше мы... Хорошо, давайте заведем дерево отрезков на этих значениях, только на этих индексов, которые будут обновляться. И все. Но как бы... если мы получаем какой-то запрос, да, то мы просто обращаемся, то мы создали для этих значений массив отсортированный, да, мы отсортировали их по возрастанию, и значит, что если мы получаем запрос какой-то, 1.7, допустим, да, в этом массиве, мы ищем помощью binary search, мы ищем левую и правую границу, да, индексов, а потом вот узнаем вот эти индексы, да, 1 и 2, допустим, и у нас, так как у нас построено дерево отрезков на этих индексах, на вот этих индексах, мы можем легко узнать ответ. Вот, допустим, вот 0, что там, ну, какие-то элементы лежат, да, и вот под ними индексы. Точнее, вот так, да, какой-то А, 1, 2, и 3, 2. И вот мы, где-то мы, ну, вот мы узнали вершинки. We calculated for this vertex answer, like, and that's it. We just when we get answer, we get answer. Сейчас. And for example, we just plus it to our sum. Before we start, we remember a full array, and e equals to what? E equals to indexes that E not in indexes, in A indexes, and we just calculate this non-updated values. We just sum all non-updated values. Okay. In some cases, this modification is very useful. For example, you can do this modification or this modification. If you know, it will be better if you do this, not this, because in this case you got complexity like O of size A array that I considered. No, array can be if you update some endpoint, if just 1 second, if list is if updates happen in point, you get just all query complexity. Ужас, интернет. All query complexity. Okay. Do you have questions? Then now, no, I think. Okay. Next data structure. Next is persistent data structure. Persistent data structures. Data structures. What is it? Persistent data structure is data structure without this data structure that always contain all the versions of changes. I mean, reverses the previous version of itself. When it's modified. Okay. Examples. You have. Как это можно понимать? How can we understand it? We suppose nodes are versions and edges are updates. We update our data structure somehow. We have only update operation, and we have only versions. Okay. How can we store all versions? We can remember these edges, for example, these modifications, and if we this is the case, if versions are not modified, we just remember this edge somehow. Хорошо, good. In other cases, we otherwise. Сейчас, otherwise, хорошо. We want to, if we do update, we can modify these versions. We can сейчас. Not this. We create version with this update. Сейчас. updated version with update. And then we just copy the edges and create new version. We have on each update we have some edge, and it can be, for example, GitHub works like we use this idea. Okay, and third case, that's a lot of memory. Сейчас. 1 second. For each update, complexity will be like no, on, and memory creates on memory too. So third case, we just want to update. We just want to suppose only one edge, one ветку, one pass. We do update. When we do update and replace this, we just delete this update, and we just, or just, we can do it in array, I think. Okay, we can do it in array. We just replace all the values. Okay. Да, we just replace all the values. Сейчас как бы так выделить. Replaced. Okay. And memory will be O1, O1, I mean, and in every time in this example we get O n to the ONK, ON queries. In this example we get ON. So but we consider only one. We consider examples only one case. Хорошо. Persistent array. persistent array. Suppose we get some array. Suppose we consider array, and we want to do update. We consider first case when we update only updates. I mean, we can create only edges on the end. This kind of updates. Consider update iteration, and in some pos, and we consider what? Get by version in some position. So okay, how can we create edges? How can we create updates? We just for each position for each how can we effectively store our persistent data structure? We can contain all the vertices, but in this case we contain only list of updates in some point for each element. For each element we store a list of changes. We store a list of edges, and for example, for some position in this array, we get lists of pairs. List of pairs. And not list, we create ordered for each pos. List of changes, not list of changes. Так, list of changes implemented on ordered map with case of versions and values of changes. it's simple. We just when we want to find some versions, for example, we we initialize our array, and sometimes we update. Sometimes we do update. In 7 iteration, we do update, some update on this point. In 9 iteration, we do some update. And we want to get version. We want to get. We need to know what чему равнялось значение. Сейчас. On some version. То есть, I mean, if we get query, not get, just get 5 in post 6, post 6, post 6, да? Post 6. We get an ordered map. In this map we take example 8. We take upper bound. Not lower bound. We take lower bound. Take lower bound. 6, 8. Okay, and get 7 elements. Okay. Why can't we use unordered map? Because we have the same problem in previous, in this. In this task we get the same problem. We can't if there are numbers that we can remember, in which we can remember positions, we just do binary search in this array. And in this example too, we just do binary search of 6, and we get this pair. Wait, of 8, and we get this pair. I think it's normal. If I don't сейчас. Если не узнаю фразы все, которые мне нужны для английского, мне очень плохо рассказывать. Хорошо. Good. In this case we get like O log n complexity because binary search. and we get updating some posts, we get 01. Okay. Next data structure, persistent stack. We just store list of all tops in versions. Сейчас. Of all tops of versions. Ну, that's very easy, I think. Ну, if we consider some stack, if we pop, for example, 5. Okay, there will be stack and some array. When I push 5, we add in this array 5, 6, we add this array 6. Push. Then we, for example, pop. push, pop 6. Not this. Так. We pop and get 5. That's all. Just contain this list. There is no optimizations, I think. Так. You can think about how to implement it in these cases. No, it's obvious if I consider this. If I consider some. If I have already explained meaning of persistent data structure, I think. Okay, and next, finally, persistent segment tree. There's a little interesting. Тут немного интереснее, because we consider, for example, update. Just update on some point x, and we consider get sum of some LR of some version of a segment tree. Okay, let's think how to implement this edge more effectively, in more effective way. We can store our segment tree. For example, when we initialize, we have only root we have only root. We just I mean we get segment tree. Okay. We don't consider any optimizations. We build segment tree based on array. Then if we do update, if we do update at some point, for example, we just create another segment tree with this update. Not segment tree, we just create changes. For example, we just do +6 in all the nodes, and we create this. Как там сейчас? We create this pass. Okay. Big segment tree. If get update, if get update, create pass, of changed values. Okay. And if we want to if we want to get sum on some segment, we consider we launch. Okay, if we can, for example, weather, we consider if we want to go to vertex that not existed in our update, we just we want to get last update of this vertex. Get update of last vertex of last segment. No, segment that corresponds this vertex. And we okay, how can we implement? We can iterate through all these updates and find this vertex, but we can do it easily. How? Is there anybody? We just when we create update, if we consider this vertex before, and we want to сейчас, 1 second, I think about this. If we consider changes in root, we just want to, if we, for example, want to get query that considers this vertex, what we do? We just want to get like this vertex. Okay, but we just delete and provide it like this. Get pass. So how to do it? How to do it? How to do it in okay, when we create pass, when we create some pass, we want we just all empty edges we just provide to we just link to we just link it to we just link it to vertex in previous versions, but okay, we can do it for all of we can find this vertex. We can find this vertex if we consider versions. If we consider versions, we can find and nodes and roots. And for example, we want to update this vertex, and we just okay, and we just and this vertex didn't change. And we just do it for ON, but notice that we want to if we want to go to this child doesn't exist. This will be link on this will be link on right root, for example. Once again, once again. We consider it's ON, but we want to do it for O1. We want to call this vertex for O1. How can we do it for O1? Okay, when we if we find this vertex, we just we go like this. But create a link like this. Okay, if we consider another version of some array, we just go like this, then this, then I mean then this, and get this. I think it's clear. Okay, and we get O1 instead ON, O of count of versions. Okay. There is another two segment trees, two modifications. But I consider only one, I think. As I explained in this task, consider we want to implement this task by using persistent segment tree. We don't do we don't make fractional cascading. We do just what we do. Consider problem. Okay, consider problem. Just problem. Calls it like problem. How can we call it? Fractional cascading problem. Fractional cascading. Fractional cascading problem. Okay. Consider fractional cascading problem. Okay, we can create persistent tree on every update. I mean, if we get some sequence, we can sort it. The sequence, and then we 1 second. Then we sort this we sort this array, then we iterate, then we create segment tree, and we create segment persistent segment tree with nulls with n zeros. So, and we iterate through A, and to update the PST with uh, with A values. So we get sequence of we get persistent trees. I think I mean we get segment tree on each version, and if we got some segment, just 1 second. Okay, I think about this a little bit. Just excuse me. There are a lot of people. Get some updates. Okay. Do you want to in every segment tree? Okay. 1 second. Okay, if for example iteration 3, suppose we get 1, 3, 5, so on, yeah? And we consider version if we can and x, our x equals to 5, and we want to calculate sums on this. Нет. Want to calculate only this. We want to calculate only this values. And how to do it? We just launch binary search. Binary search on versions. We know all the versions, all the updates in each version. And and then we sum these ranges. Then we calculate just sum of all these ranges. Okay, we find some version in this version. We launch. We launch just как? We just count. We just launch usual get. With count, because for example, for this tree 1, 2, 3, for example, now for example now, so now 1, now 3, 5, and we want to get counts. We just get it for all log n. That's all. All n log n. We get memory like all n log n, and complexity will be O n, O log n, just O log n there, because we get log n operations when we do binary search. Сейчас. And then we do binary search, when we then get usual query with count function. That's all. That's all I think. Thank you. We'll consider multidimensional segment trees in next seminar.